This video is on balancing redox equations. When you balance a redox equation, you balance for two things, mass and you balance for charge. This equation that you're looking at might look like it's balanced because if you look, you might say, well, there's one zinc here and there's one zinc here and there's one copper here and there's one copper here. And what that means is this reaction as written is balanced for mass. What's not balanced for is charge. Because if you add up the charge on the left-hand side, you've got something that's neutral, which has a charge of 0, plus something that's got a charge of +1, and 0 plus 1 is 1. If you add up the charges on the right-hand side, you've got something that's an element 0 plus 2, and 0 plus 2 is 2. So the two sides don't have equal charge, so this is not a balanced redox reaction. And you can always check to see if a redox reaction is balanced. We're checking that they are balanced for both mass and charge. So the way we balance this is something called the half reaction method. What that means is we show the oxidation and we show the reduction, and we balance the half reactions first. We balance those both for mass and charge. Now the first two reactions I'm going to do as examples, the half reaction will be balanced for mass and will not be required balancing for charge. But then I'm going to show you how to do that as well. So here we go. So we have zinc 0 turning into Zn plus 2. And that's our oxidation half reaction. And we have Cu plus 1 turning into Cu copper atoms. Right? So copper ions becoming atoms and vice versa. Now, we're going to put now these are balanced for mass already. There's one zinc on both sides, there's one copper on both sides, but they're not balanced for charge. And the way we're going to balance these for charge, I'm just going to put this little 2 in there, is we're going to place electrons in the half reactions. And we're going to make it so that the charge on the two sides are the same. Now, the one critical thing about this to remember is electrons have a negative charge. So if you have one side with a higher number on it or a higher charge, that's where the electrons are going to go. Watch how this works. So if I take zinc 2 plus and I add 2 electrons to the right-hand side, and you think of them as each electron is -1, you then have 2 plus -2 equals 0. So the right-hand side now is equal in charge to the left-hand side. Now, a good general thing to just memorize, if you want to memorize things, is in oxidation, the electrons will always be on the right-hand side. They will always be on the side with the higher number. So 2 is higher than 0, so the electrons are going to be there. For the copper, the reduction reaction, or reduction half reaction, we will always have electrons on the left-hand side if it's reduction. And if you think of it as if I put one electron here, 1 plus 1, or -1 plus 1 equals 0. So I've just balanced those two. Those two half reactions are now balanced for mass and charge. And now what I'm going to do is I'm going to equalize the electrons lost and gained by doing something to one or both the equation, which means multiplying it. And then I'm going to add them back together. Before I do this, I'm going to do just a little quick erasing of these numbers up here, these ones that I put in here, because I want to get rid of those. All right. And I'll put the Zn back in there. All right, here we go. So the common multiple of 2 electrons and 1 electron is 2. They both go into 2. So I'm going to multiply the bottom equation by 2. And when I do that, I'm going to distribute that 2 to everything in the parentheses. So I'm going to put a 2 here, a 2 here, and I'm going to turn the 1 electron into 2 electrons. And then I'm going to get rid of this outside 2. And what I'm now going to do is I'm just going to add up the 2 reactions, like I'm doing algebra, like really basic algebra. So zip like this. And when I add this up, what happens is this. These 2 electrons on the left and the right cancel each other out. And what you end up having is this. You end up with 2 Cu plus 1s plus 1 zinc with no charge gives you 2 copper with 0 charge plus 1 zinc with a charge of +2. Now there's 1 zinc on both sides and there's 2 coppers on both sides. Make sure that's all 1 zinc, and that's a Z, in case that's confusing anybody. And watch how the charge works. 2 times 1 is 2. 2 plus 1 times 0, which is 0, is 2. The whole charge of the left is now 2. The whole charge of the right-hand side is now 2 as well, because 2 times 0 is 0, plus the 1 zinc, which is +2, is 2. So this is now balanced for both mass and charge. Let's try doing this one, the next one. I might go a little bit faster. I'm going to very quickly write down the half reaction. So I've got Al turning to Al plus 3. And I'm going to put my electrons on the side that will balance them. Now this is oxidation because the number of aluminum is going up, which means the electrons are going to go on the right. And since I've got positive 3 on the left and a 0 on the left over here, I'm going to add 3 electrons on the right. That's my balanced half reaction. For my magnesium, it's going from +2 down to 0, so it's being reduced, and a reduction, the electrons go on the left. I'm going to put 2 electrons on the left. Now, 2 and 3. Now I've done 1, 2, and 3. I got to balance electrons lost and gained. So the common multiple of 2 and 3 is 6. So I'm going to multiply the top equation here, the whole top equation, by 2, and that means this becomes a 2, this becomes a 2, and this becomes a 6. By the way, you might want to do this in pencil. The bottom equation, I'm going to multiply it by 3. And so I put a 3 in front of here, a 3 in front of here, and 3 times 2 is 6. And when I add these together, my net equation is this. These cancel out. And now I'm just going to put the coefficients in the equation above it instead of rewriting the whole thing. The Mg's both have 3's in front of them, and the Al's both have 2's in front of them. And watch that switch. 3 times 2 is 6. 2 times 0 is 0. So the whole left-hand side is a charge plus 6. On the right-hand side, 2 times plus 3 is 6. Right? And there's a 3 in front of the Mg is 0. And so this is now balanced for mass and charge. All right. Now, so far, we haven't had to deal with balancing for mass first before dealing with balancing for charge and half reactions. So I decided to do one in which that was not the case. So here's one where it's not the case. So I'm going to write out my 2 half reaction here. I've got Na arrow, Na plus. I'm going to not balance this for mass yet. I'm just going to write out the 2 half reactions. The other one I have is Cl2 arrow, Cl minus. Now, of those 2 reactions, one of them is not balanced for mass, and that's the one on the bottom. Now, this is the one that's really important because sometimes students see things they see patterns in the first ones I do, and I want you to avoid just looking for the pattern and recognize the reasoning behind it. So I'm going to put a 2 right here, and now I'm going to have to put electrons in here. Now let's make sure we're clear on what's going on here. This first one here is still our oxidation because it's going from 0 to +1, and this is definitely our reduction. So electrons are still going to go on the right-hand side for oxidation, the left-hand side for reduction. Now the top reaction is already balanced for mass, and we just put our 1 electron here to balance out the +1 here. This is the one where you have to be careful because students get used to saying, well, this is right, the difference is 1, but it's not. If you really understand this, you have 2 chlorines, each of which is gaining 1 electron. And if you think of it, 2 times -1 is equal to -2. The charge on the left-hand side has to be -2 as well. So in order for this to be balanced, I'm not going to put 1 electron over here. I'm going to put 2 electrons because -2 plus 0 equals 2 times -1. So that is, those 2 equations are now balanced. Those 2 half reactions are balanced for mass and charge. And now I'm going to multiply my 2 equations and put the coefficients when I add them up back on top. Now, since there's 1 electron, 2 electron, I'm going to multiply the top equation by 2. So I'm going to put a 2 here, a 2 here, and turn this 1 electron, 2 electron, and then I'm going to add them up. Now, the electrons are going to cancel each other out. But look what happens. The 2 ends up here, the 2 here, just like in the equation, I just took these and put them here and here. This stays a 1 right here, but this becomes a 2, which means it is now balanced for mass and charge. And I can check it. 2 times +1 is 2. 2 times -1 is -2. 2 plus -2 is 0. And these guys were all zeros to begin with anyway. So therefore, the 2 sides have a total charge of 0. That's balancing redox reactions with half reactions. Now, I thought it was really important to do one more thing, which is to balance just some half reactions, because this shows up, this is a more likely thing to actually show up on the regents in the multiple choice, and I think you should be able to do this. So I'm going to go through these so you're prepared to do the castle learning. For each of these, you should first look at it. I would pause it and try to do it, and I'm going to put up my answers. I'm going to label all these as reduction and oxidation first. Then I'm going to put all the numbers into balance, all of them for mass, and then I'm going to balance them all for charge. So I'm pausing and writing that. Okay, so the first one's oxidation because it's going from +2 up to 3. The second one's reduction because it's going from +4 down to +2. The third one is going from -3 up to 0. That's oxidation. So it doesn't matter if it's negative or positive. How is it changing? Is it going up or is it going down? The next one is going from 0 to -1. That's reduction. The next one's going from 0 to +3. That's oxidation. The last one's going from +7 down to +2. Now I'm going to balance these ones for mass, for those that have to be balanced. By the way, this has got to be either. I messed up. All right. So the first one is balanced for mass because one Fe on both sides. There's one Sm on both sides. There's one N on the left and two N's on the right. So I'm going to, because of the diatomic thingy, right? So I'm going to put a 2 in front of here. I've got to put a 2 in front of here. And that's going to change the numbers of electrons, right? The letter E and F are both balanced for mass as well. Now I'm going to put the electrons in to balance them. Now, what students who were trying to come up with a shortcut often just try to match the number of electrons on the side where you put the electrons with the number up top, and that doesn't work. So for the first one, I got +2 on this side, +3 on the right-hand side. So I am going to put in, I'll pause, 1 electron, because 3 plus -1 is +2. For the next one, I'm going to put electrons on the left-hand side. Whenever it's reduction, they go on the left-hand side. So I'm going to get rid of these O's and R's here. Just make it easy, give myself a little more space. Right? I know I'm going to have to put my electrons over here for the next one. And since 4 plus -2 will be equal to 2, I'm going to put 2 electrons on the left. The next one's a hard one. The total charge on this side is -6. The total charge on this side is 0. So I have to make the charge on the right hand side equal. So believe it or not, I have to put a total of 6 electrons on the right-hand side. The next one is another example of reduction. And again, I'm going to look at what the total charge is on the two sides. This side is 0. This charge is a total charge of -2. So I've got to make the left-hand side have a charge of -2 as well, which means I'm going to have to put 2 electrons over here to add to my 0. For Al0 to Al +3, that should be easy. This is the one where you can just match it up, and that works nicely, but only when you're going from 0 to a number or a number to 0. If you're going between numbers like the last one, this is a charge of +7 on this side. This is +2, right? What number do I have to add to 7 to make it 2? I have to add -5. I have to add 5 electrons. So I'm going to put 5 electrons on the left here. Notice, the number of electrons doesn't always match the little number up here, right? So sometimes this number here matches this number. But what really is happening here is we're making sure that the charge on the two sides are the same in a half reaction.